In this lesson, we're going to look at another mathematical concept with vectors called the cross product. If the dot product was all about measuring how much two vectors agree with each other, how much one vector points in the direction of another, the cross product is the exact opposite. The cross product doesn't tell you how similar two vectors are, it tells you how different they are. It gives you a new vector, one that's perpendicular to both of the originals. The cross product doesn't give you a number like the dot product, it gives you a vector that points out of the plane where the two vectors are, that the two vectors lie in. And I know we haven't talked about planes yet. We're going to get into that in the next unit. But imagine it if you have an X and Y coordinate system. It's just all of that coordinate system is considered the plane. So let's think about this. So if two vectors lie flat on a table, the cross product points straight up or straight down. If two forces are acting on an object, the cross product helps us determine the torque or the rotational effect. If you're building a video game or 3D animation, the cross product tells you where a surface is facing and how objects know which way is out. So why do we care about this in calculus? Because this is where vector math starts to connect deeply with physics, engineering, computer graphics, and more. It's not just numbers anymore, it's direction, rotation, and space. So in this lesson, we're going to learn how to calculate the cross product both algebraically and geometrically. And then once you're comfortable with that, in the next lesson, you're going to explore applications of this cross product in real world scenarios. So this kind of math is the math that shapes what's really happening around us. So let's take vectors and add more to what we already know to create something new. So the cross product is also called the vector product. It's called that because when I have two vectors and I'm crossing them, I end up with both a magnitude and direction. We write the cross product as one vector cross a second vector. So this would be read U cross V. And the cross product of two vectors yields a vector that's perpendicular. So it is perpendicular to both of the original vectors. So therefore, it's only defined when we have three-dimensional space. We can't define it in two-dimensional space because that third dimension, that perpendicular vector, is going to either come out of or into the page, into that 2D plane. So the formula to find the cross product geometrically looks fairly similar to how we were finding the dot product geometrically, except in this case now, we have the magnitude of U times the magnitude of vector V times sine of the angle between them. And it's this little n right here. And it's a unit vector. And it's a unit vector that's perpendicular to both U and V. And if you've taken physics, you'll be familiar with the idea of a vector that's perpendicular to a surface being the normal. And that's actually what n stands for, is normal. So it's a unit vector that's perpendicular to both of the other vectors, the normal vector. And it tells us what direction that U cross V, or those two vectors, the cross product, is facing. Again, there is a right-hand rule for this. So to find the direction of U cross V, we're going to use another right-hand rule. You're going to curl your fingers from U to V, and your thumb is going to point in the direction of U cross V, of that perpendicular vector. I've included a little bit of a video just to explain it a little bit more, and so you can see it visually. But if you wanted to think about it, if your fingers are pointing in the direction of the vector U and you curl them towards vector V, your thumb is going to be pointing towards you. That means that the positive direction of n is coming out of the page. If we were doing it the other way and we had our fingers pointed in the direction of V, you would see that you have to turn your hand upside down. So now your thumb, as your fingers are curling from V to U, your thumb is pointing into the page, and we denote that as the negative direction. So go ahead and watch that other video if you feel you need a better explanation or a visual explanation. And we're going to, so go ahead and watch that video, and then we're going to dive into what we need to figure out this cross product. Before we move on to doing any of the math, I want to take a second just to point out some properties of the cross product. So the rules for the cross product are similar to the algebra rules, but we have to remember the cross product is not just multiplication. There is more going on there. So two that I have written here are two that we should be very familiar with because they are the same as they are when we're just doing anything algebraically. The first one is this distributive property. The distributive property. So if I have a vector crossed with two other vectors that are added together, it doesn't matter if I do u cross v. I can distribute it out. U cross v plus u cross w will be the same thing as u cross v plus w. The second one there is that the order you multiply a scalar by doesn't matter. So if I have k times vector u crossed with v, that's going to be the same as vector u crossed with k vector v, which is also the same as saying k times vector u crossed by vector v. Now there's a couple more that I want to add onto this list. So I want you to think about this idea that if I have u crossed with v, that is going to be equal to the negative of v cross u. They're opposites. And this is exactly what's happening if I have two vectors and I reverse them. The direction is opposite. You can think of that negative as being the opposite direction. The other one is this idea that the magnitude of u cross v is actually equal to the area of the parallelogram that's defined by u and v. So it's equal to the area of the parallelogram. Don't judge my inability to spell parallelogram. Parallelogram. Oh, there, I think I got it right. Area of the parallelogram defined, which just means outlined, by u and v. So what does that look like? Well, if I have vector u here, and I have another vector v here, with some angle theta in between, if I extend this to create the parallelogram, this is u, this is v. This whole area in here is really what we're finding, when we have u crossed by v. That's the actual magnitude of it. That's what we're finding is the area. So let's go ahead and let's look at a geometric example. Okay, so just as a reminder, the formula for u cross v is equal to the magnitude of vector u times the magnitude of vector v times sine of the angle between them. And now it needs a direction, so it's got that unit vector n. And just as a reminder, unit vector n will be positive if it's out of the page, according to the right-hand rule, and it will be negative if it's into the page, according, again, to that right-hand rule. So here's our magnitude, and here's our direction. Okay, so let's take a look at an actual question. I'm going to make this a little bigger. So now that we've seen the formula again. So we have two vectors. Vector u, the magnitude of vector u is 30. The magnitude of vector v. So here's vector u right here, and it has a magnitude of 30. Here's vector v, has a magnitude of 20. The angle between them is 40 degrees. And u and v are in a plane of the page. So they're lying flat on the table, and we need to figure out, well, what is u cross v? So really, we're trying to find a perpendicular vector to both u and v. So we're going to write out what our formula is. Let me make this a little bigger. Write out what our formula is. So we have the magnitude of u times the magnitude of v times sine of the angle. Now we need to figure out this direction. So we need to know what direction is it going in. So I'm going to use my right-hand rule, and I'm going to put my fingers in this direction, and I'm going to curl them towards the other vector, which means my thumb is coming straight up and out of the page. So that means that using the right-hand rule, my directional normal vector is positive. That means it's coming out of the page. Now all we have to do is fill in the numbers. So the magnitude for vector u was 30. The magnitude of vector v was 20. The angle between them is 40 degrees. And this positive vector n just hangs out on the end. It's simply telling us that the direction is positive out of the page. When I put that in my calculator and do some calculations, I get it's approximately equal to 385.7 in the direction of positive n. Now, if we want to reverse it and do v crossed with u, our direction is now into the page. So now we're going the other way. So now we've got, I'll do this in a different color. So now we've got our fingers running along V, and we are curling our fingers towards U. Well, the only way that I can do that, unless maybe you're super double jointed, I don't know. The only way to do that is if my thumb is now pointing into the page. So my thumb is pointing into the page, not out of the page, which means that for this one, my N will be into the page, which means it's negative. And that's going to tell me what direction it's going. So we have V crossed with U is going to be equal to, this time, the magnitude of vector V times the magnitude of vector U, which we know is exactly the same, times sine of my angle. And this time I have a negative direction. So we can fill all these in. We have 20, this time times 30, sine of 40 degrees, and our negative n. And we get negative 385.7 n. All I did was move that negative up in front. We really didn't need to do all of this since we already had a right-hand rule that tells us, and this actually kind of proves that it is equal to the negative value. So we really didn't need to go ahead and do all of this, but it does prove it. So u cross v is indeed equal to negative v cross u. Like I said, just like with regular vectors, we reverse the direction. If you reverse the direction of the vectors, you reverse the sign. So now that we've seen it geometrically and we have an idea of what's going on, let's look at it algebraically. So remember, when we have an algebraic vector, and now we're firmly in the 3D world, so we have triples. So if I have a vector u, this is my x, this is my y, and this is my z value. Same thing over here for vector v. I have an x, y, and z. We've just changed how we're talking about them a little bit. U1 will be my x value for vector u. U2 will be my y value for vector u. And U3 will be my z value for vector u. Same thing over here. So if I have u cross v, I'm taking the difference between them. So I have v2 u3, so v2 times u3 minus u3 times v2. That will be my x point. My y point will be u3 times v1 minus u1 times v3. And my z point will be u1 times v2 minus u2 times v1. If we wanted to rewrite that as using these unit vectors as scalar multiples of the unit vector, we could write it like that. I don't want you to panic about this. You don't actually need to memorize this. There's absolutely no need to, because there is a little bit of a trick to it, and I'm going to show you what that is. Your textbook does it slightly differently, but it's the exact same idea, so we're not going to worry that it's not exactly the same. Okay, so if I have vector u crossed with vector v, I'm going to go ahead and I'm going to write out, using these values up here, I'm going to start by listing the components that are in vector u, my x, y, and z, but I'm going to start at the y. So I have u2, next would be u3, then I circle around to u1, and I'm going to end on the same one that I started with. I'm going to do the exact same thing for vector v. v2, v3, v1, all the way back around to v2. Now, if we take a look at our formula, maybe you'll see where I'm going with this. So my x value will be equal to the cross of the top and the cross of the second one. So it's u2 v3 minus u3 v2. My y values, now I just go down the row and I cross again. My y value will be u3 times v1 minus u1 times v3. And last but not least, my z values will be u1 times v2 minus u2 times v1. So again, there's my x value, u2 times v3 times u3 times v2. My y value, u3 times v1 all over u1 times v3. And my z value, u1 times v2, u2 minus u2 times v1. Now let's try it. So here's an example. Let's determine u cross v if now u is equal to 1, 1, 1. There's my x, there's my y, there's my z, and vector v is 2, negative 7, 3. There's my x, there's my y, there's my z. We're going to follow the exact same process. U cross v. I'm going to write it up here. Okay, let's see. I think I have enough room. I'm going to make this a little bigger. Okay, so again, I'm going to start here and I'm going to list out my components of vector u. So I have my y component, my z component, my x component, back to my y component. Now they're all 1, so this can look a little confusing. Now on v, vector v, I'm going to start with my negative 7. I'm starting with my y component, and I'm working my way through. 3, 2, back to negative 7. So now if I want to know u cross v, I am going to go ahead and cross them. So my first value, my x value, will be 1 times 3 is 3, minus 1 times negative 7, so minus negative 7. That's my x value. My y value will be 1 times 2, which is 2, minus 1 times 3, which is 3. There's my y value. Last, we're going to do our z value. 1 times negative 7 is negative 7, minus 1 times 2, which is 2. Negative 3 minus negative 7 is really 3 plus 7, so that becomes 10. 2 minus 3 is negative 1, and negative 7 minus 2 becomes negative 9. So there is u cross v. That is our new vector of u cross v. So now the next part of this question says determine a unit vector that's orthogonal to u cross v. Well, the unit vector will be orthogonal to u cross v. So really, orthogonal, remember, means perpendicular. And when I'm finding the cross product, I'm finding a vector that's perpendicular. So if I have u cross v, and I want to find the unit vector for that, I'm going to divide it by the magnitude of u times the magnitude of v. Well, we already know u cross v because we just figured it out up here. So we have 10, negative 1, negative 9. Now we need to figure out the magnitude part. And remember, the magnitude for any vector is just using that Pythagorean theorem, a squared plus b squared plus c squared. Or if you want to think about it in terms of x, y, and z, x squared, y squared, z squared. So let's do vector u. So my magnitude of vector u is 1 squared plus 1 squared plus 1 squared times the magnitude of vector v. And vector v, the magnitude of that is 2 squared plus negative 7 squared plus 3 squared. So that gives us 10, negative 1, negative 9, square bracket, all over 1 squared plus 1 squared plus 1 squared is just root 3. And 2 squared plus negative 7 squared plus 3 squared gives us a root of 62. That gives us 10, negative 1, negative 9, all over, now remember, we're going to multiply these together, all over the root of 186. Now, we're not quite done there because we need to know a unit vector that's orthogonal, so we need to break this up into its actual components. So it will be 10 over root 186, negative 1 over root 186, and negative 9 over root 186. Okay, so that's it for this lesson. Short and sweet. There are some practice questions from the textbook, so take a look at those. And if you have any questions, feel free to send me an email.